Swayam Prabha. Digital India. Educated India.
Arguably the most important topic in neural networks. Now, we would like to dive deeper into feed-forward network and backpropagation, and also look at applications of feed-forward network. So, just reminding ourselves that natural language processing has areas which can be represented through true concentric circles, and this is inspired by the AI area diagrams normally given in different textbooks of AI. So inspired by that, we can say that NLP has these very useful areas which touches our lives, like machine translation, information extraction, information retrieval, question answering, multimodal access to information, sentiment, emotion analysis. All these are represented in the outer circle because they affect our lives and interact with our day-to-day activities. They're the areas which are impactful in our life and society. But these areas need to draw their core techniques from rule bases, logic, search, learning, and so on. So machine learning and NLP are very synergistic these days. But early days of NLP spent a lot of time and energy in creating rules. For example, creating rules for machine translation. When we translate from English to an Indian language, we have to bring the verb to the end. Okay, Delhi is the capital of India. Is in the middle of the sentence. So subject, verb, object is the structure for English, but in Hindi the verb will go to the end. Delhi Bharat ki Rajdhani hai. So is has become hai and has moved to the end of the sentence. So these kind of rules would be required for transforming one sequence to another. So sequence to sequence transformer has always remained a very important concern in natural language processing, but now we have techniques for sequence to sequence transformation. Logic is important. Entailment, for example. So we want to see if a piece of text is consistent with another piece of text. Delhi is the capital of India. Administrative decisions for India are made in Delhi. So these two sentences are consistent with each other. Search is required because we normally have many hypotheses alive as we go along. And one of the hypotheses becomes the winner hypothesis by having the largest probability. And machine learning, of course, we are seeing all along. We have seen hidden Markov model, conditional random field, maximum entropy Markov model, now neural networks. So, this matrix we have seen before, and we are spending time on the last column, which is the deep learning technique. And in that again, dense feed-forward network with backpropagation, softmax. This is our concern. And the problems, of course, are always there in our perspective. We, in detail, looked at the problem of pause, chunking, and parsing. Some techniques in parsing are remaining to be discussed, but that we'll do in context of neural network. So dependency parsing, how to get the dependency tree of a sentence. So that requires a technique, and this technique amenable to neural network? We'll see that. One important question remaining is the efficient computation of probabilistic parse trees. So the parse tree which has the highest probability is the output from a probabilistic parser. Okay, so now to compute the highest probability parse tree, we have to compute a max function. We have to generate all parse trees, compute each of their probability, and then give the winner parse tree finally. But parse trees have huge amount of sharing. From one parse tree to another, there will be lots of subtrees which are common. So for efficiency, we can make use of pre-computed subtrees and use them in a new parse tree. So that is a dynamic programming situation. And the inside-outside algorithm for probabilistic parsing is meant for doing that. Then there are words and disambiguation, machine translation, semantic role leveling, sentiment, question answering, discourse processing. All these are important problems related to text, and we need techniques. And many of these techniques are neural network based. It is also good that many of you have very interesting projects. And in these projects, at least a part of these task versus technique metrics, you will be able to address. Now, we would like to delve deeper into feed-forward neural network, look at applications of feed-forward neural network and backpropagation. And we should start discussing sequence processing, which is important, let's say, in machine translation. We convert sequence in one language to a sequence in another language, obeying the lexical transformation and the syntactic transformation. And then recurrent neural network is the. We would like to look at some applications of feed-forward neural network. Start with a very live application, very practical application in NLP. So this is something which came from one of my consultancy projects. This is an example. An example SMS complaint. I have purchased a 80-liter Videocon fridge about 4 months ago when the fridge go to sleep at that time. Compressor give a sound, cut, 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 cut. What is it? Can't understand. Give me the text. Sentences give a sound. Speak in India, making use of this kind of onomatopoeic sounds, words. Onomatopoeic words are those which are reminiscent of the real life phenomenon. Okay, Garajna, for example, Garajna is the Garajna of cloud. Okay, so this is reminiscent of the sound that the cloud makes. So this is a very Indianized way of making a complaint about a refrigerator. This is absolutely a real complaint. You can see this kind of complaints on online fora and the customer feedback that is taken by e-commerce companies and even e-governance. Everything online can get customer feedback, and they are expressed in the form of text with pictures, and many times the sound also can be recorded. So the whole thing can be very multimodal. You process the image, process the speech signal, process the text. Now, this says that I have purchased a 80-liter Videocon fridge. So that is the main component, one of the main components of the communication. And the time spent is 4 months ago. So look at the information extraction process that is going on, which human beings almost effortlessly do. So Videocon fridge is an entity. The capacity of the Videocon fridge is 80 liter, numerical entity. Important action here is purchasing. I have purchased. Purchase is the main verb. 4 months is a numerical quantity, needs to be taken note of. Then in 4 months itself, the refrigerator has started giving problem, and the fridge go to sleep. The fridge go to sleep is a very very appropriate expression, very apt expression. It exactly says what the fridge does, but it is not really idiomatic English. This is an Indianized English text, and the compressor give a sound. Okay, this cut, 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 cut is also making the problem absolutely clear. This is what human beings do. However much we control the language behavior through grammar, through different kind of prescription of good language, people will communicate the way they find it easiest to communicate. What is possible fault over it is normal, I can't understand. So the person wants a solution for his problem. Please help me, give me a suitable answer. So he also wants a textual answer. So a chatbot might look at this SMS complaint. Would actually, not might, would. Many organizations have their chatbots. And you have to do dialogue processing, which is a very important natural language processing problem, and engage in an interaction with the chatbot through this kind of situation. Now, this is a very realistic natural language processing situation relevant to our country. And if you go to Nigeria or maybe Finland or Thailand, English will be expressed influenced by the culture and syntax of language spoken, written there. So language any language gets influenced by any other language. This is a very interesting phenomenon at the border of two states or at the border of two countries. Okay, so this is a situation, and now we begin to look at the important entities. So this is called information extraction. I have purchased important verb, 80-liter Videocon fridge entity, 4 months numerical entity, freeze go to sleep is the problem, compressor give a sound, cut is another problem. Then asking a question, this takes us to question answering. What is possible fault over it is normal. So the person is not expressing himself or herself clearly, but I think the problem is understood. An intelligent human being will be able to understand and take action. So now we created a system for dealing with this kind of complaints, because the handling such complaints is not really scalable at the human processing level. So this kind of complaints come every hour for a large company like, let's say, LG, Huawei, Honeywell. So those kind of companies have problem reports coming by the hour. And these complaints have varied nature. The language is very different from person to person, full of noise, ungrammaticality. So we understood from the organization that each complaint should be categorized into these three classes: action, complaint, and emergency. Now the complaint category is probably most benign. You take the input and register the complaint. Okay, emergency is the other end of the spectrum, where the action needs to be taken immediately. Maybe from the fridge some smoke is coming out. Okay, so that's an emergency situation that has to be addressed immediately. And action is an intermediate output between the two extremes, registering the complaint, and emergency measure between them is action. So on these output classes, we did not have any control. The organization specified what output levels should be there, and the input was also not really something in our control. The input is the set of SMSs, the complaints that arrive for the organization. So here we have to process the input and give a set of numbers to the neural networks, because the neural network can deal only with numbers, a vector of numbers. Okay, and then the most important component of the problem, the total number of hidden layers and the number of neurons in hidden layer. Now, even now, we do not have any precise theory for how to design the hidden layers in a neural network. There is no theory that given such and such situation, we will have X number of hidden layers and Y number of neurons per hidden layer. There is no such theory. So this is typically done by trial and error. And as we have seen from the XOR problem, that if the situation is one of non-linearity, that is, the problem cannot be computed by a single perceptron, then we need to introduce hidden layer, just like in XOR. So the SMS is processed for a feature vector. That feature vector goes into the input layer, and in the output we obtain the categorization of the complaint. Does it require immediate attention, emergency, or is it a registration of the complaint, or is it an action which is an in-between point? So this is a network which had to be trained, and we trained them, and we saw their behavior in solving the problem. Now from here you can of course have accuracy reports in terms of precision, recall, F-score, and so on. So those things are later concerned, but I wanted to present to you an actual real-life problem situation which we have worked on for an organization, and where backpropagation and feed-forward network was used. So There are many NLP tasks to be done when the SMS is given before we send an input vector to the neural network. Now, this problem that I just now described falls in the category of text classification. Okay, a lot of feed-forward neural network backpropagation is used for text classification. The classification is a different kind of problem compared to sequence processing, where machine translation is an example. The input sequence is converted into another input sequence. So so it is useful to compare sequence processing with whole text processing, where a decision has to be made. For example, you take the whole text and decide if the sentiment is positive or negative. So that's a whole text processing situation falling under classification category. In sequence processing, we make decision at every point of the input, okay, and decide if we have to output something or just have to pass the input, do look ahead, and then output will come little later. So preemptive actions are possible in sequence processing, for example, in surveillance. So suppose a terrorist is about to throw a bomb. So the surveillance system, the computer vision system, image processing system, will look at every sequence of action for the person, and the system has been trained before with examples of terrorist attack and actions which are benign, okay, which are not harmful. So a system has been trained for harmful action versus benign action, and looks at all the sequence of activities of the person. So for example, bending, picking up something, inserting a hand into the bag, okay, drawing out something, setting a switch. So all these are actions and they are sequential actions. So this has to be processed by a machine in quick time, and the decision has to be made for any kind of preemption. Okay, so this is an example of sequence processing in computer vision, and sequence processing is the name of the game for natural language processing. So micro information is better handled in sequence processing. If we are giving my decision about a piece of text, positive sentiment, negative sentiment, so their micro information is not so much in picture. Okay, global information is important there. It is better handled in whole text processing, and chatbot interaction is inherently a sequence processing task. So sequence processing versus whole entity processing is a fundamental distinction in AI. Okay, in whole of AI, actually, it is not only a prerogative of natural language processing. It happens in many other fields: speech, definitely; vision, definitely; robotics, definitely. The sequence of action that a robot takes, or an autonomous vehicle. Okay, a driver is driving a computer is driving a car, and there the sequence processing is absolutely vital. So, let's proceed, and we take another example which was just introduced in the last class, an application in medical domain. So here the problem is there is bumpiness and scaliness of skin, mostly for symptoms gathering and for developing diagnosis skills, and not replacing the doctor's diagnosis. So doctor's apprentice through AI has been in existence for a long time, since 1970s, where people wanted to create doctor's assistant, and it was ambitiously thought that an automatic system might replace a doctor. By the way, that is possibly the case for radiologists, that is people who look at an X-ray and diagnose if there is any problem with the patient or not. So that is being automated big time, very heavily. In fact, we are also involved in this automation. I have a project on this. And here the X-ray plate provides information to the automation system, and the automatic system gives decision about any kind of problem the patient might have. So this is one profession which is endangered, I would say, because it is facing the onslaught from automation. Okay, similar is the case with highway driving, by highway driving by trucks. Okay, trucks go on highway driving. The driving is typically very smooth. You essentially have to navigate. Essentially, have to navigate. So there, the automation also is threatening a profession. So so here we have a problem with the condition of the skin, and there is bumpiness, scaliness, and these symptoms are gathered. So the architecture of the feed-forward neural network is, this is a problem we saw about 15 years back. Okay, but the problem has not become really irrelevant. It comes exactly in the same shape in many other medical automation situation. So 96 input neurons, 20 hidden layer neurons, and 10 output neurons. So inputs are skin disease symptoms and their parameters. So these parameters are location, where is the malady seen on the skin, the distribution, the shape, arrangement, pattern, number of lesions, presence of an active N order, amount of scale, elevation of papules, color, altered pigmentation, itching, pustules, lymphadenopathy, palmar thickening, results of microscopic examination, presence of Herald patsy, result of dermatology test called KOH. So this is completely out of bounds for a computer scientist. Okay, this is absolutely deep medical knowledge, which the computer scientist is not really trained to process. We do not know. For example, I do not know what is lymphadenopathy. I do not know. But doctors and medical experts would know all these, and they would give us, the computer people, the AI researchers and engineers, these possible symptoms, these possible input parameters. Okay, so without this interaction of computer scientist with the domain expert, it is impossible to solve any problem. So the domain experts need us. We need the domain experts. Without that medical knowledge, I would not know. Absolutely, I would not know what is to be input to the neural network, the feed-forward neural network. Okay, and the fact that these these features are important came from decades of experience of medical knowledge, decade of experience of medical practice. Okay, so skin specialists, skin doctors have done these observations year after year, decade after decade, and have codified this knowledge for the benefit of other practitioners, other fields. So when we do automation, when we do AI, NLP, computer vision, speech, we just cannot lose sight of the knowledge that is present in the problem and the domain. Otherwise, we are just moving in the dark, okay, like a blind man, guided by nothing except for the computing machinery. Okay, just the computing machinery, and that is of no value absolutely without the knowledge coming from the domain. So here the skin disease symptoms and their parameters are given. This comes from medical expert. Now after that, things become tractable for automation. So we take 10 neurons indicative of the disease, because the disease classification is also given by the medical expert. So there are these psoriasis, pityriasis, rubra pilaris, lesion planus, okay, pityriasis rosea, tinea versicolor, dermatophytosis, cutaneous T-cell lymphoma. All these are disease conditions for the skin. Okay, and we do not know what they mean, but we know abstractly that these are classes for us for a machine learning system. But how is psoriasis different from pityriasis rubra pilaris? That is known to the doctor, and it is important for me as an AI engineer to know this difference. What is the reason? The reason is that I cannot do error analysis when I look at the results. It is impossible for me to do any kind of error analysis and do any kind of improvement based on the insight, okay, without this kind of medical knowledge. So that's why when we do natural language processing, we examine the output from a machine transform system, question answering or sentiment analysis system, unless we understand the behavior of the text, unless we have insight into how language operates, it is impossible to do any kind of improvement of the system through error analysis. Okay, so it is not enough to understand the sigmoid function, softmax function, backpropagation, or the maximum entropy model. No, not enough. We need to have a deep insight and strong grip on the problem itself. In NLP's case, it is language and text. So 10 neurons are indicative of the diseases. So it is a 10 class problem, 10 output class problem, which comes again from the medical experts. We won't know. The AI engineers will not know. Okay, so we do not know what the input should be. We do not know what the output should be. Once these are given to us, we can design a computing system for solving this problem. So both parties need each other. Both the worlds need each other. So when we design this system, this duration of lesions, the number of weeks that came as an input to the input layer, minimal etching, I don't recall now, it is really some time back, why there are two neurons with the same input. Durations of lesions, weeks, duration of lesions, weeks, it came twice. Minimal etching, positive KOH test, lesions located on feet, minimal increase in pigmentation, positive test for pseudo hypho and spores. Bias is the threshold for the whole feed-forward network. So this was designed, and there were many more neurons in the input layer. I think there were 96 neurons, as I mentioned. Then there were 20 neurons in the hidden layer. This is where doctors had nothing to do, or medical experts could not do anything here. This layer is completely in the purview of computer scientists. Okay, how many hidden layer neurons should be there, and how to train them, how many hidden layers should be there. This is now in the purview of the computing expert. But here again, there is a kind of intuition which is at play. That intuition are these neurons able to do some kind of clustering? For example, pilaris and psoriasis, do they belong to a kind of clustering? So this points to a kind of taxonomy in operation. So we take these diseases and begin to cluster them and begin to create a tree structure. Okay, so medical disease, and then 2 or 3 sub branches, and then each branch has number of sub branches. So this is called the taxonomic representation, and this kind of taxonomy is also called knowledge graph sometime. Okay, and this knowledge graph often decides how the architecture of the neural network should be, and if you extract the embeddings from the knowledge graphs, then they can substantially augment the power of the neural network. So this is some research we are very deeply into in our lab as to how this kind of taxonomic information can assist the deep learning system. So internal representation at that time, 15 years back, remember, I remember doing this internal representation by means of some kind of taxonomic insight into the disease that the skin doctors talked about, and they really brought in just absolutely impeccable insight into how the medical knowledge should be organized. Okay, so this was very instructive, and the output layer is very obvious. The number of diseases, each neuron is responsible for a particular disease. So if the symptoms are for psoriasis, this neuron will become 1, other neurons will be 0. Okay, so this becomes the winner neuron. And now we know in softmax computation, what happens is the output is now no longer 1 or 0. It is some kind of probability value. One probability value is more than other probability values. And the training should be such that the winning probability should be really at a good distance from the other probability values. So the training data, the input specs of 10 model diseases from 250 patients. So At the time, this looked like a huge amount of data, but hardly. If by today's standard, we got data from 250 patients, and 0.5 is some specific symptom value is not known. So if the output is if the input is 0.5, then we do not know a particular symptom. For example, let's say the blood pressure of the person is not known. Then we just put 0.5 there. And we trained it using standard error backpropagation. So the testing was done on previously unused symptom and disease data of 99 patients. So correct diagnosis could be achieved for 70% of papulosquamous group skin diseases. So the diseases were grouped. You can see there is one group called papulosquamous. So 70% precision was obtained for this class of diseases. Success rate above 80% for the remaining diseases except for psoriasis. Psoriasis is diagnosed correctly only for 30% of the cases. And the reason is that psoriasis resembles other diseases within the papulosquamous group of diseases and is somewhat difficult even for specialists to diagnose. Okay, so there was a kind of mirroring of human capability by the backpropagation network. Okay, wherever human beings did well, the backpropagation network also did well, and on very limited amount of data, just 250 patients records. So this also means possibly there is a lot of underlying regularity in this particular problem, especially the taxonomy is possibly very well structured. So this was the observation obtained, and the doctors were pretty thrilled that this kind of assistance can be obtained from an automatic system. And in recent times, one of my MTech students, Tanay, has worked on adverse drug reaction. So if you administer a particular drug on a patient, then will the patient get adverse drug reaction? So this is the famous ADE problem, adverse drug extraction problem, where again we have used deep neural network and pretty high accuracy for that. So healthcare medical informatics is really a good test bed for a lot of deep neural network work. Now, when the diagnosis comes from the feed-forward network system, so doctors asked us, why is the network giving this explanation, especially for error cases? So this required explanation ability, and explainability, today is a very hot topic. Everybody wants to know what is the deep neural network doing internally. So neural networks actually this kind of neural network which is giving decisions on a particular problem is also called a connectionist expert system. Rule-based expert systems are those where rules are embedded, and connectionist expert systems solve a particular expert situation problem by neural network. And the neural network should really explain the decision, especially if it is a medical domain problem. Especially if it is a medical domain problem, because there are people's lives and risk to life is involved. So the hidden layer represents the data, as is well known, and in deep neural networks, everybody talks about representation of the data and the concepts. So the input layer represents the input data, and the hidden layers represent the data. And the output of the hidden neurons are neither symptoms nor decisions. So the hidden layer does not interact with the environment at all. It represents the data and sends the representation to the output layer for further decision making. Now, the symptoms and parameters contributing to the diagnosis were found from the network. Standard deviation, mean, and other tests of significance used to arrive at the importance of contributing parameters. So which input parameters are really important? So this is called ablation study. So you switch off that particular input parameter and see how it affects the accuracy. So for example, is the blood pressure of the patient important for skin disease detection? So that you can see by switching off that neuron. I mean, make the input to that neuron 0 and see what is the effect on the error. This is known as ablation study. And the whole network can be looked upon as acting like an apprentice to the expert. Now, here we come to an important discussion, which is hard max versus soft max. So you can see in the neural network for this skin disease detection. Here, if the person has psoriasis, then this psoriasis neuron will be on. Other neurons will be 0. Okay, so that is for the training data. In test data, after the new situation is taken, then there will be probability values for each of these neurons. Okay, psoriasis is probable with, let's say, 85% probability, and other things are lower probability, but all of them should add to 1. So this kind of decision making is called softmax. If you have hard 1, 0 values in the output, then this is hard max, and softmax is a value which is not really 1, 0, but something between 0 and 1, but clear neuron probability values. Now, soft much more. Most decisions are. In fact, in medical, you see it happening much more. The softmax decision is much more, and the doctors internally operate with the probability. Most likely, I think this person has jaundice. Most likely. Okay, so this kind of softmax decision is actually reality, and it has to make use of probability. Okay, now we go back to our technique again, the feed-forward network and back propagation. So a very representative problem for XOR is the for feed-forward network and back propagation is the XOR problem, where the input neurons receive x1 and x2 values. They come in the shape of 0, 1. And we know that for 0, 0 output should be 0, 1, 1 also output should be 0. And for the two other inputs, the output should be 1. So this is impossible to be computed by a single perceptron because there is an inherent contradiction in the data. Okay, 0, 1, 1, 0 output should be 1, 0, 0, 1, 1 output should be 0. So single perceptron cannot deal with this situation, which it thinks is a contradiction. Okay, now the XOR problem can be solved by a kind of decomposition. So x1, x2 are given, and x1 bar x2 is computed at hidden layer neuron number 1, and x1, x2 bar is computed in the other hidden layer neuron. Then a OR is computed. OR network is very simple. You just put the two weights as 1, and each of these weights should exceed the threshold. But even if each of these weights should be such that the input exceeds the threshold when any of the inputs is 0, 0 or 1, sorry. And if both are 0, then it cannot exceed the threshold. So this is the OR network. Threshold is 0.5. W1 and W2 are 1 each. X1 bar, X2 and X1, X2 bar are computed by this kind of weight arrangement. The thresholds are 1, 1. Minus 1, 1.5, 1.5 minus 1. These are the weight values coming from x1 and x2. And these neurons can compute x1 bar x2 and x1 x2 bar. So this then gets fed into the outermost layer and the result comes out. I had mentioned that there is an alternate way of doing this computation. You can also compute x1 plus x2 and x1 bar plus x1 plus x2 bar. X1 bar plus x2 bar is nothing but the NAND function, x1, x2 bar. So you can apply Boolean algebra and see that this is true. Now this network actually computes slightly differently. It computes by ANDing at the outermost layer. Now for ANDing to happen, the weights can again be 1, 1. But OR threshold was 0.5 and threshold is 1.5. So none of the inputs individually can exceed the threshold, but combining together, they can exceed the threshold, which is a property of the AND function. And you can compute XOR function. You can compute the OR function with 2 1s and threshold is 0.5. And NAND function. So just negating all the input parameters. Negating all the parameters, that is weight values become -1, -1, threshold becomes -1.5. you can compute NAND function. Okay, so just think about this point, that if in Boolean logic, if you have a network, if you have a perceptron compute a particular Boolean logic, its complementation will be handled by, can be computed by negating the parameters. Is this true? Just think about this question. So this exercise, Satyam or whoever is taking the exercise, please put it down. And and Jyotsna, please add this as a slide after the exercise is given. Is it true that in that the complement of a Boolean function can be computed by a perceptron by negating all the parameters, all the weight values and the threshold value? Is this true? So just take a look at this. So these are two different ways of computing the XOR function, either AND of intermediate computation or OR of the intermediate computation. Now, so we had specified an exercise for you that you should implement backpropagation for XOR network and observe if it converges. Error should fall below a limit. Now, what does convergence mean for backpropagation? You see, we have total sum square error at the output layer, and the total sum square error should can never be completely zero because of the nature of the input-output function. Input-output function is a sigmoid, and the sigmoid function, the sigmoid function is this: y is equal to 1 by 1 plus e to the power minus x, and the derivative of the sigmoid is just y into 1 minus y. This is what makes the sigmoid function interesting, because the derivative is very simple to compute. It was also found long back that sigmoid actually mimics the behavior of a neuron. Okay, that means this saturation behavior that the sigmoid shows when the input is large, that is what happens in the brain also. A very interesting remark is made here. So it is often seen that in case of intense emotion, people sometimes faint. Okay, the brain stops its activity in case of intense emotion. Say in case of intense grief or intense surprise. Apparently, the brain tries to protect itself from intense transfer of electrical signals and amplification of electrical signals in the brain. Okay, so if that kind of signal happens, then you can have some kind of brain stoppage, which is, I think, called thrombosis, coronary thrombosis. Coronary is heart. I don't remember the exact name for this kind of brain functioning stopping. Okay, and that happens when in case of intense emotion, and intense emotion is reflective of very intense activity. Activity is just electrical signals, okay, inside the brain, the neuron firing or not firing. So medical knowledge tells us that brain has this internal mechanism of saving itself from intense activity which is damaging. And this is possible because the neurons can saturate inside the brain. Sigmoid is a function which saturates for high value of the input, and that people say are reflective of the actual behavior of the neuron. So anyway, y equal to 1 by 1 plus e to the power minus x has this kind of saturation behavior. Okay, the neuron, the sigmoid neuron becomes 1 at plus infinity and 0 at minus infinity. So there is a two-way saturation possible for sigmoid neurons. So you can see that the sigmoid neuron can never reach 1. It can never reach 0. So the value of the neural network will never be actually 1 or 0. But the target output is desired to be 1, 0. Okay, if the sentiment is positive, it should be 1, otherwise 0. So then it is always described by means of an error limit. The error limit should be below, let's say, 0.1 or 0.01. And this is what is the meaning of convergence of a feed-forward backpropagation network, unlike perceptron kind of convergence. So the exercise that was given to you is to implement the XOR function and check if it converges. That means if it brings down the error value below a particular level. And you were also to examine, are the input neurons computing XOR by x1, x2 bar and x1 bar, x2, or are they computing this by performing OR in one hidden layer neuron and NAND in the other hidden layer neuron? Do please implement backpropagation for XOR and do this kind of investigation, which will sort of cement your understanding of feed-forward and backpropagation neural network. Now, a neural network can also represent important information in NLP. This is an indicative diagram. So you give the input, maybe the next layer does morphological analysis, next layer does part-of-speech tagging, next layer does NER, and so on and so forth, and finally the decision is obtained at the outermost layer. We also need to understand very clearly batch learning. Batch learning is updating the parameter after one pass over the whole data set. And incremental learning updates parameters after seeing each pattern. And epoch is one pass over the entire data set. So if I take the example of XOR, the data set is V1 000, V2 011, V3 101, V4 110. If the weight values are changed after each of these VI, then this is called incremental learning. If the weight values are changed after one pass over all VIs, then this is batch learning. Okay, so this is the definition which we need to be very clear about and keep in mind. And we also know that perceptron training algorithm cannot be used for feed-forward neural network simply because the hidden layer neurons do not have the output, and therefore misclassification is not known at the hidden layer, and therefore you cannot add the failed vector to the existing weight. So I think I'll stop here now and take questions for the remaining 10 minutes.
Yeah, sir. So Anish was asking, wouldn't a decision tree model have been a better approach for the skin disease case? Is there a reason neural network was used?
I think very good question. So let's go there. Okay. So this is the right question. Why should we employ a particular technique for a task? This one question which we should always ask before solving a problem. Okay. It is fashionable to take up deep neural network for solving a task, but are we underdoing or overdoing in terms of technique? Now, this is one problem where how does the decision tree operate? So decision tree operates by making decisions at every node. Okay, so I take the 96 parameters, 96 symptoms, right? The input symptoms and their combinations. So each symptom is represented by a node in the decision tree. So in each decision tree, I examine the value of, for example, location of the disease, and I have a set of values. Okay, and then depending on where that location is, I take that branch and then ask question on the next symptom, which is distribution. Keep doing it, and then finally arrive at the decision for the actual disease. Now the problem is that the decision tree is also nothing but a rule base actually. Okay, it is a representation of a rule base. If condition, then action. So action is branching to a particular node, and finally the action is hitting the leaf and giving the decision. So now the problem is actually characterized by lot of noise in the input. So rule-based systems are great if everything is hunky-dory. Okay, all symptoms, all inputs and outputs are very clearly specified. There is no uncertainty with respect to decisions. Okay, every class is very cleanly separated, 1-0 class. But this is not the case for most of the real life situations, and the input data is typically beset with all kinds of noise and incompleteness. Okay, incomplete data was a characteristic of our problem situation. Sometimes the shape is not known. Sometimes etching value is really very fuzzy. Okay, so many values were noisy, fuzzy, and sometimes incomplete. Rule-based systems are not really geared up to deal with this kind of situations. So we decided to go for neural network. Is it okay, Anish?
Yes, sir. I got it.
Okay.
Thank you.
Any next question?
So,
There are no more questions, sir.
sir,
Yeah.
yeah, means basically decision trees are not robust to outliers, is it?
Decision trees are not robust to outlier. What do you mean by outlier?
Sorry, I mean, there is some mistake in the so, features.
Yes. Yes. So yeah, outlier is not the right term. So as I said, noise is the right term. So the values are not always trustable, and sometimes values are not given, and you have to be robust against all this. And decision tree is nothing but representation of a rule base. Rules are great when everything is in.
Yes, sir. Thank
Okay, so if there are no more questions, then maybe I do a little bit more progress with our lecture material. I still have 5 minutes. So we go to the backpropagation algorithm as such. So backpropagation, you recall, sets the weights for input to output. So I need to fix this weight Wji, which will be required for the input to output mapping. Now we saw that gradient descent is the main technique for doing such things. So delta Wji is minus eta into partial derivative of error with respect to Wgi. Make sure that you understand this starting point clearly. We obtain the parameter values by looking at the influence of that parameter value on the error. Okay, that's why this influence is obtained by taking the partial derivative. How much does change in a particular parameter value change the error itself? So error is known because it is a supervised learning situation. In unsupervised learning situation, we do not know the error. So see the nice approach to the problem that the weight value will be found out by measuring its influence on the error. This is called the credit assignment problem. Okay, a very fundamental idea in machine learning, whole of AI. So suppose a project has succeeded. Now the management has to reward employees. So which employee was critical for the project? He or she should get the maximum, let's say, bonus for rewarding the success. Similarly, if the project has failed, which employees were mainly responsible for the failure? They should be punished or penalized the most. So this is the blame transfer situation. So what we are looking at now, that delta Wgi is equal to minus eta delta Wgi, partial derivative of E with respect to Wgi, is nothing but the credit assignment problem. And we are multiplying it by the learning rate because that decides the speed at which the iteration progresses. And the whole thing is an iterative algorithm. You initialize Wgi and then find out at every step by how much it should be changed so that the error reduces. The error reduces because of the property of the gradient descent law. So in gradient descent, we have delta Wmn proportional to minus delta E delta Wmn. So you can see here, if the derivative is positive, then there would be a decrease in the current weight value. So delta Wmn is negative. Delta Wmn. So if delta Wmn is positive, that means that if the slope is positive, when is the slope positive? If the E increases with Wmn. If Wmn is increased at that point infinitesimally, then error also will increase. That's why Wmn should be decreased. Okay, and therefore Wmn should be decreased, and therefore the change in weight should be negative. So positive gradient means the change in weight is negative. Similarly, if the gradient is negative, then the weight should be increased because delta Wmn is positive. Is this intuitive? Yes, because if you increase the weight value, the error would decrease, and that is what we want. Okay, so this gradient descent law ensures always that the error decreases at every step. Therefore, the backpropagation algorithm can be seen to be a greedy algorithm. It has no way of increasing the error and then coming down again unless you do some randomization on the weight values. So this is a case of greedy approach to parameter fixing. Okay, so we'll stop here today and again meet tomorrow. Thank you then.